Hello class, this is Mr. Gonzalez here to simplify your lives just a little bit more than they, well, let's try and make it simple. Alright, so I'm not going to answer any particular problems from worksheet 4. I'm going to leave that up to you guys, but I am going to show you guys how to do problems that are on there, but I'm not going to give you the actual ones. So these are going to be problems very similar to them, okay? So, let's get through this. So one of the problems is an incline problem, and we're going to have problems with objects being acted on at different angles. And so this is an example of something being acted on by at an angle, alright? So, let me show you exactly what we need to do. Now, first things first, when we're given a problem like this, let's just say that we're asked for the acceleration of our block as it goes down, okay? That's ultimately the majority of what these questions are going to ask for. And so first things first is I'm going to draw a little diagram here just to show, hey, looky. Alright, well, okay, that's probably a little silly to say, but look at this. We got a gravitational force going down, and you're going to have the normal force that goes perpendicular to the surface. Okay? In some problems, you might find a friction force going against it. Okay? So, in one of the in worksheet 5, you'll see that, but in worksheet 4, you won't. So, I'm going to copy this. Cool and cool. Alright, now one issue, and the issue is, well, we need to write our free body diagram. Alright, so I'm gonna put my gravitational force right there. I'm gonna put my normal force right there. Now, you could very easily have done the same thing by doing the normal force first and then doing the gravitational force second. As long as if you look at what I did is I can't zoom out anymore. Is I grabbed the same vector, I placed it right there, grabbed the same vector, just put it there. Or I grabbed my same vector, put it there, same vector, put it there, whatever. Okay? What you're gonna see is, okay, we are missing something, and we're missing something actually very important. And we're missing a side of our triangle. Oh my gosh, this is terrible. What can we do? This is so tragic. I don't know what to do. Wait, look. What we were doing before is we were grabbing it from one end and we were showing, oh look, it'll come down like that. Or object will come down like that. Because if you look at it, the object's going to fly down the ramp exactly like that, right? And I think I need to draw this just a little better. Okay. And then so this one also shows that it goes like that. And that's what the acceleration's going to do, right? That's what the acceleration's going to do, right? The acceleration is going to go down the ramp just like that. Okay? So, when you have this and you have acceleration just like that, remember, the net force vector goes in the direction of the acceleration. So I'm going to erase A, I'm going to erase A and keep net force, because remember, the net force vector goes in the direction of our forces. Okay? Okay? The net force vector goes in the direction of our forces. So, you need to remember that the angle of our incline always goes between the gravitational and the normal. And so the angle of our incline always goes between the angle of our normal force and our gravitational force. Normal and our gravitational. So, what we see in either of those is, well, when we find our acceleration, we have forces, we're going to want our net force divided by our mass. And so we just want to find that net force there. And so when I try to find my net force, well, this is my angle, this is my side opposite of my angle, and this is my hypotenuse, which is my gravitational force. So what I'm going to do is I'm going to say that's my opposite, that's my adjacent, and this is my hypotenuse. And so opposite and hypotenuse, well, if you write out SOHCAHTOA, oh man, I can't write. If you write out SOHCAHTOA, you know that sine has to do opposite over adjacent. So your sine of your 30 degrees is equivalent to your sum of the forces divided by your gravitational force, because it's your opposite over your hypotenuse. So your sum of the forces is equivalent to your gravitational force multiplied by the sine of 30 in this problem. Okay. Then next, I look at my gravitational force. I look at my object, and it's a 5 mass object, 5 kilogram mass. So the gravitational force is 50 times sine of 30. And I believe, I sure hope it's not a terrible number. If it is, I feel pretty darn bad for picking 30. Oh goody, it's 1/2. So, 50 times 1/2, and so we get 25. So my net force is 25 newtons, and my mass is 5 kilograms, so my acceleration is 5 meters per second squared. That turned out very nicely. It turned out a lot better than I thought it would. I chose a really good angle. So, that's how we solve for that. Alright, notice how I'll come over it again a little bit later. Okay, so let's come over here. We have a pulley. This represents a similar problem to one of your problems on your worksheet. So, if you're right here, this is the gravitational force here would be 40 newtons, and the gravitational force here is, and I'm going to label this gravitational force of A and gravitational force of B, is 30 newtons. So, well, let's see what happens here. If I were to draw my diagram, you would basically look at it and see, well, this one is heavier than that one, right? So because this one is heavier than that one, it's going to accelerate downward that way. Alright? So because this one's going to accelerate downward that way, this one's going to accelerate upward that way. So if I draw my diagram for A, what I'm going to get is I'm going to get that my gravitational force should be larger than my tension force. Okay? And I'm going to get that my net force for A is this guy. Let's do for B. Well, for B, as I said, the gravitation force is going that way, but the acceleration is up. Alright. This mass right here, B, it wants to go upwards because it's connected by the same string, and so the string is going to pull this one down and this one up. So, I'm going to draw this guy at a decent size. Maybe here. Maybe this would be appropriate. Okay. But clearly, we have a tension force that has to be a bit larger, probably. So, my tension force might want to be this guy. Keep in mind now everything's drawn to scale. Okay. And then this right here is my sum of the forces for B. Alright. Now, this tension force is the same as this tension force. Okay? They're just not drawn the same length because, well, that'd be a little tedious to draw them the same length and try and figure that all out. Okay? Only thing I just wanted to demonstrate was that the tension force was larger than the gravitational force, which is what was which is why it kind of like pulls it up that way. Otherwise, it would be falling down. All right, because we needed some way for the net force to be upward for this one. So what I'm going to do is I'm going to say, well, okay, we want the acceleration. And for the acceleration, we can do it either any of two ways. You have the net force for A is equal to the mass of A times the acceleration. And you have the net force for B is equal to the mass of B multiplied by the acceleration. Now, why are these two the same acceleration? The reason is because it is the same string that's pulling them. And so both objects have to accelerate in the same way. Okay. So what I'm going to do is I'm going to look at this and say, okay, well, that right there is the same thing as those two added right there. So my gravitational force of A equals to my sum of the forces of A plus my tension. Okay. I'm also going to say that my tension is equal to my gravitational force of B plus my sum of the forces of B. Okay. Now this gets a little interesting here. Okay. So what I do is we have tension right here. We have tension right here. So we're going to substitute this whole thing in right there. So I'm going to rewrite it up top. Okay. I just substituted. This was the tension force. Now it's this. So now, if I remove my parentheses, we would see that if we want our sum of the forces, we want the sum of the forces for these two, right? So we want to subtract this guy to get him to the other side. So we get my sum of the forces of A plus my sum of the forces of B equals my gravitational force of A plus the gravitational, no, I subtracted gravitational force of B. Okay, I'm gonna plug this guy in, this guy into here, and plug this guy into here. So I'm going to get the mass of A times the acceleration plus the mass of B times the acceleration equals to the gravitational force of A minus the gravitational force of B. I'm going to factor out the acceleration. I'm going to get acceleration on its own by dividing both sides by the mass. And so what I'm going to do is I'm going to plug in my numbers now. My gravitational force of A was 40 newtons. B was 30 newtons. The masses together was 7 kilograms, so it's 10 divided by 7. And so I put that into my calculator, I get 1.4. Oh, sorry. So I plug my stuff in the end. I got that. So clearly, when we do the sum of the forces, it's the sum of the forces plus the sum of the forces, all right, for both A and B. And I'll go over the little tricks later again, okay? All right, last problem. I need to get through this last one. All right, so now what's gonna happen is this guy's gonna drag you down, all right? Meanwhile, this guy's gonna move that way, okay? So I'm going to start off by drawing my thing for B. Since the acceleration is downward for B, I should have my gravitational force for B to be longer than the tension force. And then what I'm going to fill in this spot with is, since the acceleration is downward, my net force for B needs to be downward. Okay? From this, I get that my gravitational force of B is equivalent to my net force of B plus my tension force. Okay, now let me draw my little diagram for A. For A, we're ignoring friction. So when I ignore friction, what I'm going to get is I'm going to get a tension force that way. I'm going to get a gravitational force that way. And I should complete it with the normal force right here. Just to show that, yes, there's a normal force and a gravitational force. These two should be the same length. Okay. And so we are missing something here, alright? And there's no friction force, so my acceleration is that way. Acceleration's that way. Alright, so next, after this, then I'm going to say, okay, well, my net force for A equals to my tension force. That's cool. So what I'm going to do is I'm going to substitute in right there. Substitute in. So my gravitational force of B equals to my net force of B plus my net force of A. We need to remember that net force for B has to do with the mass on B times the acceleration, and the net force for A has to do with the mass of A multiplied by the acceleration. So when I plug them in right here, then I get my gravitational force of B equals to my mass of B times my acceleration plus my mass of A times my acceleration. I'm gonna do the work down here and say, if I factor out the acceleration, I get my masses equals to my gravitational force on B. Alright, then mass of A, mass of B. We're dividing both sides to get rid of those. And then so then that cancels out. So I get that my acceleration to be my gravitational force of B divided by, when you add my masses, well, B was 2 kilograms, so it's about 20 newtons. And then mass A and mass B is 4 in that, so them added together should be 6 kilograms. And then so if I do 20 divided by 6, then I get, whoops, I did that wrong, 3.3 meters per second squared. Okay? Okay, now I'm going to go over everything that I did, and hopefully you can catch up. This is just reiterating the work that I did. Let me separate the two problems over here because it's a little bit of a mess of what I did. Okay. Okay. So, for our incline problem, we didn't really have any friction. We ignored friction. And so all we had was the gravitational force going down and the normal force going off to the side. So I redrew them into my free vector diagram with the gravitational force going down and my normal force still going in the same direction. So I did as I said, where's my fingers? My fingers are right there. I said bring this guy and just drag him down there. So he goes in the same direction, same everything, okay? We were missing, we had a gap right there. And when we had a gap right there, we're like, okay, well, our block is going to be sliding, down the ramp. It's going to be sliding down, that way. And so because it's sliding down that way, then I completed my diagram by showing that the acceleration has to go that way, so the net force does that too. Okay. Now, next, I said that the angle of the incline, that 30-degree incline, we always put it between the gravitational force and the normal force. Okay. So we put it there, and then we said, okay, well, if we look at our triangle, we have our gravitational force is our hypotenuse, and then we have our opposite side of the angle is our sum of the forces. So we used sine equals to opposite over hypotenuse, and then we said sine of 30 equals to opposite over hypotenuse. We solved it, and we got this net force to be 25. And then so when I plugged in net force equals 25 and my mass was 5 kilograms, we got a nice number of 5. For the pulley, what we did is we drew our forces and we said, okay, if we look at our forces, what we have is we have, if we look at our forces, then what we have is we have the gravitational, our mass A is going to be heavier than mass B. So at mass A is going to be pulling down, while mass B is going to be going upward. So I showed that the acceleration downward for A is larger than the acceleration upward. Alright? And so that's why the gravitational force is larger than the tension force when I draw it. And then I completed it by showing that the mass A is accelerating downward right there. But for B, all I was showing is I was just showing that the tension force has to be larger than the gravitational force. For B, because mass B is actually going upward, and so the gravitational force is not big enough to keep it going up. And so I show that the gravitational force, the sum of the forces for B goes up because mass B is going to be moving upward. And so I wrote down the sum of the force equations for mass A and B, and I wrote that the length of gravitational force of A equals to those two added together. Cool. The tension force is equivalent to those two added together. Cool. And I recognize that these two are the same tension. Why? Because it's the same rope. It's the same string. Okay, so I did a substitution, and after I did the substitution, I did the work, and I did substitution, I did the work, and I said, well, those two are both sum of the forces, so I'm going to do sum of the forces plus sum of the forces gets us what we want. So, next, afterwards, then what I'm going to do, then I subtracted that from both sides, and I said, okay, this is fantastic. Look at this. We have some of the forces on one side and the gravitational forces on the other. And I substituted, and I got that guy over there. I factored out the acceleration, and I divided by the addition of the masses on both sides, and I got my calculation to be 1.4. I mean, sorry for the shaky cam, and I apologize for in and outs. And then for the last problem, what I did is I basically showed that, hey, if you look at mass B, B is going to be accelerating downwards, and A is going to be accelerating to be the right. So since B is going to be going downwards, the gravitational force needs to be larger than the tension force. And I completed my diagram with the net force going down because the acceleration is downwards. And then for A, what I did is I showed that the normal force and the gravitational force of A should be the same because it's on a flat surface. And then the tension is going to the right, and we're just ignoring friction, right? So because we're ignoring friction, we don't have friction in there. But we had to complete the square. So in order to complete the square, we put the net force of A to be going to the right because the acceleration of our block is going to the right. And so I wrote my equation so that to say that the length of T, or the tension force, is equivalent to that. Cool. But then we also have right here that the gravitational force of B equals to those two. So I did a substitution. I got this. I did another substitution again. And then in the end, I showed that the acceleration is equal to my gravitational force of B divided by my masses. And when we did the math, it turned out to be 3.3. Now, I need to reiterate. These are not the answers to problems on the worksheet. These are examples showing you how to do them, and it'll help you with the worksheet. Now, good luck, and I will upload this soon.